34 notes here, working on examples like this, where we have two horizontal changes. So again, these are both horizontal changes because they're inside of the squaring, so that identifies them both to be horizontal. I'm going to quickly do our setup here of get our parent function, f of x equals x squared, make our table of values, and graph that. And our dashed line. So that's all done. So I'm actually going to, just as a heads up here, first walk through this the wrong way, the way that it seems like it should work, but it ends up not working. So if you want to wait to write it down and just kind of see how this works, you can do that. So it seems like we should go in here and say that our factor of 2 and a plus 4, we should call those a compression by 1/2, because again, horizontal things always work backwards. So if it's multiplied by 2, we'll use that reciprocal and say instead half. So compression by 1/2, and again, because it's plus 4, working backwards would be a shift left 4, and this would be horizontal compression by 1/2, which means as we work through our table of values for our transformed function, our y values are actually going to stay the same because there's no vertical changes, but our x values are going to change by multiplying by 1/2 and then shifting left 4. And so then we would take each x value, like -2, multiply it by 1/2, and then subtract 4. 1/2 times -2 would be -1, minus 4 would be -5, and again our output values will stay the same. Instead of keep going this way, I'm just going to verify that point right there. So again, we, based on the transformations that we think are happening, think that an x value of -5 should have an output of 4. So I'll go into the function and plug in -5 and actually see if I get 4 out. So 2 times -5 would be -10 plus 4 and then squared. So that would be -6 squared. Yoys would be 36, which is not what we thought it should be of 4. So there's something wrong here with the transformations that we assumed. So we have to go back and address what we've done. And so the piece that we have to actually go back and address is how we approach these transformations. And we actually, when we see two horizontal changes like this, we have to take a step in between. We have to first, whatever value is sitting on the x, we're going to factor that out first. So it'll be 2 times x plus 2 squared. The reason this works this way is because we're saying in this function we want to whatever happened at -2, so this value to now happen in our transform function. So this input part here has to come out as -2 in order to get a 4 out. So we have to work backwards here, even more so. So instead of just a horizontal compression by 1/2, that's going to stay the same because of this 2. But instead, now we're going to have a shift left 2. We have to factor out that piece first. So then going in here, if I have 1/2 times -2, instead of subtracting 4, I'm going to subtract 2. So this is 1/2 times -2. It's going to be -1 minus 2 is -3. should change it up here too. And so then if I go in and verify with that number instead, so instead of -5, I wanted to use a pencil here, but it didn't show up on the overhead. Oh, no, we'll leave that +4. So I'm going to go verify now that -3 has an output of 4. So f of -3, if I plug that in, so 2 times, again, back into this original function. Always go back to the original. So 2 times -3 plus 4 would be -6 plus 4. -6 plus 4 is -2, and then -2 squared would give us the 4. So the moral of the story is, if you see 2 horizontal changes occurring, whatever the value is that sits in front of the x, you have to factor that out first and then identify your transformations. And so now going back down through here and finishing this up, we have 1/2 times -1 minus 2. So -1/2 minus 2 is going to be -2.5. 1/2 times 0 minus 2 is going to be -2. 1/2 times 1 minus 2, -1.5. And 1/2 times 2 minus 2. Again, just going through each of these x values and transforming them is all I'm doing. 1/2 times 2, 1 minus 2 is -1. So then my transform function should have a point at -3, 4, -2.5, 1, -2, 0, -1.5, 1, and -1, 4. And that would be our transformed function. Again, just to see another point verified, I'm going to come down here just to show another verification here. So I'm going to pick another point that we're saying should be on this function. So like -2. So going back up to that table of values, I said that -2 should have an output at 0. Again, that's just going from right here. So if my transformations are correct, -2 should have an output of 0. So if I plug in -2, again, I'm going to go back to the original function and do 2 times -2 plus 4 squared. 2 times -2 is -4 plus 4 squared. That's going to give us 0 squared, which is 0. Which is what we said in the table of values based on our transformations. Again, I was just verifying another point since this was a little bit different. And just showing again that this idea that it has to be factored out, so it's 1/2 minus 2 instead of 1/2 minus 4. Alright, so then these practice problems here, just going to work on how to factor out that value. So in A, again, seeing both a horizontal stretch or compression and a shift, we're going to factor out, before we identify the transformations, we're going to factor out that 3. So it's 3 times x minus 2. So then this would be a horizontal compression by 1/3. And a shift right 2. again, in a problem like B, whatever this value is that sits out here, it does not have to be a greatest common factor. It's whatever number sits in front of the x. It has to be factored out. So I have to say, what if I factor out negative 1/2, because that's what's sitting on the x. And then you have to figure out, what do I multiply negative 1/2 times to get back to a positive 4? So negative 1/2 times negative 8 would get me back to the positive 4. So then if I'm going to list my transformations, it's a horizontal, and this time because it's 1/2, it's a horizontal stretch by 2, a shift right 8, and don't forget that negative that sits out there, a reflection. And since it's a horizontal reflection, so it has to flip this way. If you were flipping this way, that's going to go across the y-axis. So, and a reflection across the y-axis. And then C, I put here just as a reminder that this whole idea of the factoring out the stretch compression value is only for horizontal. So again, horizontal changes are always the one that's our pain. You don't have to worry about it with the vertical changes. So I just have to go in here and do that. So it's just going to become 1/3 times 2. Sorry, 1/3 times absolute value. Again, whatever number sits in front of the x is what we factor out. So 2 times x minus 4 plus 2. So again, these stay the same. So it's a vertical compression by 1/3. And a shift up 2. And then horizontally, it's going to be a horizontal compression by 1/2. Just realized all my shifts were the same way for horizontal. Shift right 4. Alright, so again, always factor out that stretch or compression value horizontally before deciding on the transformations that have to occur. Don't do that vertically. Okay. So, if you would go ahead and try example 7 and give it a pause here, and then we can go take a look at it. Truly hope you gave it a try and paused it. I am going to hop on over and show you my work for that. So first of all, this is the cube root function. And so this is my table of values for the cube root function. And I choose negative 8 and 8 to also add on there to give me a little bit more help creating the shape of my graph. Before I identified my transformations, I first went in, and again, whatever number is sitting in front of the x in here, I have to factor that out. So I factored out the 1/2, and then as I factored out that 1/2, I had to figure out this number based on saying 1/2 times what would get me that minus 2 under there. So 1/2 times 4 gets me a minus 2 under there. So these have to be equivalent just with the 1/2 factored out. So then I have horizontally a stretch by a factor of 2 and a shift right 4, and vertically I have a shift down 4. So to create the horizontal stretch by 2 and a shift right 4, I had to do 2x plus 4. So stretch by 2, shift right 4. And then to shift down 4, I have to do y minus 4. So I went through each of my x values, multiplied them by 2, and then added 4. Went through each of my y values and subtracted 4. So from there, I then sketched my graph. And so I added on the -12, -6 over here. I could potentially add on, but at 20 I kind of went a little bit too far because I don't get to -2 too far up as I was sketching, because I shouldn't get to -2 until 20, so it should be a little bit flatter than that. So I'm going to pick a value now to go verify. So I'm going to go plug in 20. As I verify, I'm going to go back into my original function. So because if I want to catch any mistakes I made, I'm going to go back into the original. So I'm going to take the cube root of 1/2 times 20 minus 2, and then subtract 4. It's a really far away minus 4, but it's happening after the cube root. So I take the cube root of 1/2 of 20, 10 minus 2, and then minus 4. Oops, sorry. And then the cube root of 8 minus 4. Cube root of 8 is 2. Minus 4 is -2. And that's what I said should happen in the table. I said that the x value of 20 should have an output of -2. To be very honest, this is actually the second time I went through and did this video, because the first time I did it, I did a -4 here instead of a +4. And when I went to do my verifying, it didn't work out. And then I realized what I did. And so then I had to go back and make my video. So really that verifying process really can be very helpful. Alright, so there's a homework sheet for you to continue to practice these. And I will see you all tomorrow.